Today we're going to talk polar and rectangular coordinates. Now, what we're used to graphing in is our Cartesian plane, or the xy axis, if you will. And to graph a point, let's say we want to graph the point 5, 2. We go over 5, up 2, plop our little point down. Now, what we've also done recently is we've said, okay, well that point might just be on the terminal ray of some angle, and if it's on the terminal ray of that angle, we can describe it as its vertical and horizontal distance away from the origin relative to some angle theta. Now, once again, when we talk this Cartesian plane, x's and y's, all of our points will be referenced by how far over and how far up they are. But if we use this different idea of this is some angle's distance rotated around a circle and some radius out, this point here can also be described by the radius and its angle measurement from the standard position pointing east. And that's known as what's called a polar coordinate. So here's our polar, and here's our rectangular. Now, in a polar grid, looks much different than the Cartesian coordinate. The polar grid has a bunch of concentric circles, and these degree measures rotating around could go by 10 degrees as it is in this picture, or they could go by 5-degree increments, whatever. But what we're going to do is we're going to take and graph these points over on the right on this coordinate grid. So if I want to graph 5 and 30 degrees, I go out a radius of 5, 1, 2, 3, 4, 5, and up 30 degrees from there on that same radius and plot that point. If I want to do 2, negative 170 degrees, then once again I go out 1, 2, and I go all the way around 10 short of 180, which would be right here. When we start talking about negative radius measures, well, a negative radius doesn't make any sense, but negative r values correspond to rotating 180 degrees opposite the angle. So in this case, if I were to go 3 out and 20 degrees up, it would put me here. But because I have a negative 3, that says rotate an extra 180 degrees, which puts me 3 out and at 200 degrees. So once again, this is like 3 and 20 plus 180. Likewise, this last problem says if I'm going to take and go a negative 4 radius, that's like saying go 4 and add 180 degrees on to 60 degrees. So 4 and negative 60 degrees would be somewhere down here. But if I go 180 degrees opposite that, it's going to put me roughly in the 120 range. So I go from 0, out 4, and at the 120 degree mark. And those are the 4 points graphed. Now, once again, we've talked a lot about how angles can have different measures. In fact, when we look at this 2 and negative 170 degrees, we notice that it ends up at the 190 mark. And that's a coterminal angle. So we can move positively and negatively, and now that we know we have these negative r values, if you will, well, a radius really can't be negative, so there's got to be a way to adjust that, and the way we adjust is add 180 degrees to the angle given. So, given that, we should be able to name angles in several different ways. So here's a point of negative 2 and 150 degrees. Now what I want to do is name this 3 other ways using both positive and negative values for r and theta. So I want to find out where this point is first. So if I go -2 and 150, that's like saying 2 and -150 plus 180 degrees, which puts me at 2 and 30 degrees. So here's one of the 3 other ways I can name this. And if I want to look at roughly where that would be, 2 over and around 30 degrees up would be right around here. Now that's a positive angle measure. I could go a negative angle measure by going 2 out and -330. That's a coterminal angle with 30. And now what I should probably do is name this -150 in its coterminal fashion. So if I say -2, and if I'm going -150 degrees, well, the same way to say that in a positive degree measure is to go out a total of 30 degrees more than the 180. So that would be 210 degrees. So notice that would give me a total of 2 and 210 plus 180. I could subtract 180 for all that matters. But that gives me 2 and then a total of 390 degrees, which puts me at 2 and 30. So here are my 3 angle measures that describe -2 and -150 in 3 different ways. Now, in the Cartesian plane, the xy plane, I want to graph these 2 lines. And if we do that, we know x equals 5 basically looks like a vertical line at 5. So if I want to draw that graph, go vertical line through here, that's my x equals 5. For y equals -1, I go down 1 and draw a horizontal line, and that's y equals -1. Similarly, if we do this same thing relative to a polar plane, and I want to graph everywhere that r is equal to 4, well, everywhere that r is equal to 4 is basically just a circle of radius 4. So if I go out 1, 2, 3, 4, and just trace this circle all the way around, that is a graph of r always equaling 4, and the angle wouldn't matter. Now if I want an angle value of 35 degrees to always hold true, well, 35 degrees is right around here in between these two, and everywhere on this line I'm going to have a value of 35 degrees. My r will always change, but my angle holds true. Now if I continue in this other direction, I'll continue to have angle values of 35 degrees. My r values will be negative, which means that I take and add 180 degrees onto that, and I'll still have an angle value of 35 degrees all the way through. Now what we're going to do is convert from polar to rectangular coordinates. And from polar to rectangular, you'll see that if I have an r and a theta given, and I want to get my x and my y, well then I know that the sine of theta is equal to y over r, and the cosine of theta is x over r. So simply by multiplying by r to both sides, I get my polar conversions. I know that x will be r times the cosine of whatever angle I'm given, and y will be r times the sine of what angle I'm given. If I want to go the other way, in other words, if I'm given x and y values and I want to find an r value, well, my x and my y make up the sides of this right triangle. And to get r, all I need to do is use a Pythagorean relationship. Likewise, if I'm given y and x and I want to talk about the theta value, well, in this triangle, I can use a tangent ratio to relate x and y. So if I want to then isolate r, I square root both sides, and r is equal to the square root of x squared plus y squared. And if I want to isolate theta, all I need to do is take the inverse tangent. And I get the inverse tangent of y over x is equal to whatever theta value is going to be. So, once again, this goes from polar to rectangular, and this goes from rectangular to polar. Now let's take and convert some problems. I want to convert 3 and 210 degrees to a rectangular coordinate. So, if I want my x value, that's equal to r times the cosine of theta, while y is equal to r times the sine of theta. So if I take 3 times the cosine of 210 and 3 times the sine of 210, these are in degrees once again, cosine of 210 is negative root 3 over 2, and the sine of 210 is negative 1/2. So therefore, my polar coordinate goes to a rectangular coordinate, in other words, an x and a y value of 3 root 3 over 2, and that's in the third quadrant, so it's got to be negative, and negative 3/2. And in this next example, we have a polar coordinate using radians, and we want to convert that to a rectangular coordinate. So in order to do that, I'm going to take and get rid of this negative r value, call that 2, and negative pi over 4, and we're going to add 180 degrees onto that, or pi in this case. 4 pi over 4 is equivalent to pi, so this is just 2 and 3 pi over 4. So if I want to convert that to a rectangular, I say x equals 2 times the cosine of 3 pi over 4, and y equals 2 times the sine of 3 pi over 4. X ends up being 2 times root 2 over 2, and since I'm in the second quadrant, that's negative, while y is 2 times root 2 over 2. Since that's y, it's positive in the second quadrant. Thus, I end up with negative root 2 and positive root 2 as my x and y coordinate. So now I'll take and convert this rectangular coordinate into a polar coordinate. Let's think about this. 2 and negative 4 is going to be somewhere down in the fourth quadrant. So again, in order to convert that, I'm going to say r is equal to the square root of 2 squared plus the quantity of negative 4 squared, and theta is going to equal the arctan of obviously the y over the x value. So in this case, we have 4 plus 16, which is going to be 20, and I simplify that to 2 root 5. It's my r value. The arctan of negative 2 is going to give me a theta value of negative 63.4 degrees. And if they don't ask you to give values that are either positive or between 0 and 360, this would be an acceptable answer. So that is our polar coordinate. We're going to write the equation r equals 3 in a rectangular form. Well, r equals 3, we know, talked about this a little bit before, is a circle. And if I want the equation for that circle in rectangular form, I'm going to need to write the equation of that circle in terms of x and y. I know that r is equal to the square root of x squared plus y squared, and that's going to equal 3. Now typically they'll want to get rid of these square roots, so I'd square both sides and I end up with x squared plus y squared is equal to 9, which is the equation of a circle having a radius 3. So that would be the rectangular equation, if you will. Remember, rectangulars have x's and y's in them, and polars have r's in them. We're going to do the same for this equation and do some conversions in this case. This next problem is going to be much more complicated than the previous. In this case, we have r equaling 6 over the quantity of 2 minus 3 sine theta. Now, keep in mind, if I'm going to make this a rectangular problem, I need to express r's and thetas in terms of x's and y's. And I know that r is equal to square root of x squared plus y squared. And I also know that theta is equal to the arctan of y over x. But I have a couple other known identities where x is equal to r cosine theta and y is equal to r sine theta. Anytime I see r sine theta or r cosine theta, I can just substitute an x or a y in. Now I see a sine theta here, but there's no r with it. However, what I could do, what I'm going to do, is I'm going to take and multiply both sides of the equation by 2 minus 3 sine theta. Notice what this is going to do for me. I end up with 6 equaling 2r minus 3 r sine theta. The goal is to make a simple substitution for x or y whenever I can. And you'll notice right here, here's an r sine theta, which is just a y value. And 2r, I can substitute r with the square root of x squared plus y squared. And now what's going to be left to do is get rid of this square root. I'm going to bring the 3y over and get 6 plus 3y is equal to 2 roots of x squared plus y squared. Square both sides, giving me 4 times x squared plus y squared. And 36 plus 36y plus 9y squared. Distributing through, 4x squared plus 4y squared equals 36 plus 36y plus 9y squared. And you'll notice from here I can combine like terms. In doing so, what I'm going to end up with is 9y squared minus 4y squared, which is 5y squared, minus 4x squared plus 3y minus 30, or actually plus 36. And that will equal 0. And whether you remember or not, we can describe this as a function we typically know as a hyperbola. You don't have to know that right now, but this is how we want to end the problem. Next, we're going to take a rectangular equation and change that to a polar equation. So we want everything to be in the form of r's and thetas now. And notice I have a perfect square here, which I can expand. This goes to x squared plus y squared minus 2y plus 1 equals 1. I can simplify that a little bit and say I have x squared plus y squared minus 2y equals 0. Now I have a direct substitution I can make with x squared plus y squared. I know that's just equal to r squared minus 2 times y, and we know y equals r sine theta. So I'm going to make that substitution right now. Now, sometimes books will want you to leave the problem like this. Other times, and you'll just have to see what our book wants you to do, but here's one possible solution. The other can be found by taking and bringing the 2 r sine theta to the other side and dividing out an r, which gives us r is equal to 2 sine of theta. I believe our book is going to use this simplified term here. So once again, if we're changing to a polar or rectangular, you've got to make sure everything's either in r's and thetas or x's and y's, depending on what they're asking you to do.